These are the day 5 notes on confidence intervals. Today we're going to learn about our third type of confidence interval called a matched pairs t-interval and how it relates to the first two confidence intervals we've learned in class over the past few days. So a gentle reminder about when we use these different types of intervals. We learned about the one sample z interval on our first day in this unit on confidence intervals, and the one sample z interval is used when we're trying to estimate mu and we know sigma, the population standard deviation. So when do we use a one sample t interval? When we don't know sigma, but we do know s, the sample standard deviation. So what if we know both sigma and s? If we know sigma, use a one sample z interval. If you know both, use a one sample z interval. If you know sigma, use a one sample z interval. If you don't know sigma, use the one sample t interval. We're going to introduce a new type of interval today called a matched pairs t interval, which is fortunately the same thing as a one sample t interval for a mean of differences. So this is almost exactly the same setup as a one sample t interval. So when do we use this type of interval? We use this when we have two sets of data. Now everything else we've worked with so far this unit, we've had just one list of data. Now we have two sets of data, but it makes sense to compare a specific value from one list with a specific value from another list. This does require that both sets of data are the same size. So I've got a couple of examples here. One set of data deals with test scores from first hour and fifth hour, and the other situation deals with pre-test and post-test scores for 4 individuals. And the question says which of these sets of data could be used to set up a matched pairs t-interval. Again, it should make sense to compare a specific value from one list with a specific value from another. In the first set of data, if we're comparing, for example, the 20 and the 25, why would we specifically compare those two grades? They're from two different students. Other than maybe being, first in alphabetical order in their classes, there would be no other reason to compare this number 20 with this number 25. Why not compare the 20 versus the 24? We could do that as well. There isn't a specific reason why you would specifically need to compare this 20 with this 25. On the other hand, we would want to compare Birdie's pre-test and post-test scores. This is a pre-test and post-test from the same person. We'd want to compare the 42 with the 48. We wouldn't want to compare Birdie's pre-test score and Eagle's post-test score. That wouldn't make sense. There's a specific reason why we're matching up the 42 and the 48, the 40 and the 45, and etc. So that's why this second example would be a situation where you would want to set up a matched pairs t-interval. With these two lists, what we're going to do is subtract corresponding values in each set to come up with a new list of differences. So in other words, what we would want to do is we would want to, in this set of data, compare pre-test and post-test scores by subtracting one score from the other. If you're interested in figuring out how much bigger one score was than the other, maybe you would do 48 minus 42 and get 6. And then you do the same thing for all the rest of the sets of data, and you'd essentially figure out what are the scores going up by. So what we're going to do is we're going to take two sets of data, or two lists, and turn it into one. We're interested in what's the difference. What have the numbers changed by? This is the list of values that you're going to use to set up your confidence interval. Other than that, very similar to what we did in the one sample t-interval. So let's talk about what this is going to look like. Our new procedure is called a matched pairs t-interval. And if you want to add more to it, you can include for mean of differences. We are going to be interested in seeing what the average of these differences is. Usually our parameter is a mean, and that's no different here. So our parameter is going to be mu, but with a subscript of diff. This stands for mean difference. We're interested in a mean of differences, a mean difference. So when we write our parameter out, it's going to be mu diff, the mean difference in whatever, test scores, gas mileages, heights, something like that. The conditions that we're going to use today are the same conditions that we used for the one sample z interval and one sample t interval. The first condition is a random sample has been taken. And again, if it doesn't say random in the problem, you're going to say it does not say a random sample was taken, so proceed with caution. Second condition. There are three options here. Option number 1, the population is approximately normal. Look for the word normal in the problem, approximately normal. That's kind of what we're looking for. So if the population is normally distributed or approximately normally distributed, we can continue. If it doesn't say that, second option, sample size is large. Again, we're looking for a sample size that's bigger than 30. So if that's the case, say a large sample was taken and state what that number is, and that it is bigger than or equal to 30. If it doesn't say normal, if a large sample wasn't taken, skip those two and go to the third option, which is graphing the sample data and seeing if the sample data is approximately normal. If you're using our script, the normal probability plot is approximately linear, so it is not unreasonable to assume the population is approximately normal. Show a picture of the normal probability plot. If you want to make a histogram, you can use that. Just say the histogram is approximately normal, so it is not unreasonable to assume. If it's a box and whisker plot, you could say the box and whisker plot is approximately symmetric, so it is not unreasonable to assume the population is approximately normal. So pick some type of graph and then continue the statement. The formula we're going to work with today is similar to the one sample t-interval formula that we used in the past. It says x bar diff plus or minus t star times s diff over the square root of n. So we're going to be looking at a mean and a standard deviation of differences. Those are abbreviated x bar diff and s diff. In your third step, besides listing the formula, be sure and state the degrees of freedom. The degrees of freedom are still found by taking n minus 1, where n is the number of pairs or the number of differences in your list. And then in step 4 in your interpretation, very similar to what we had in the past, we are blank % confident that, if you want to include mu diff, you can, or you can just say we're blank % confident that the mean difference, you could also use the phrase mean increase or mean decrease in whatever, test scores, golf shots, gas mileages, is between the two numbers. So it's a very similar interpretation, and we'll take a look at an example on the back side of the worksheet where we're using this type of interval.